My area of research, so it is on smart grid, and I was basically completed my post graduation in electrical drives and control. But in that institution, Pondicherry Engineering College, uh, I was so much interested in the area of power system because the professors there were very much experienced, and I was very inspired by their presentations and the classes. So I want to know more. So I made myself a decision to join Anna University Research. So it is like 6 years to get a understanding on the power system. So I wish to start it from the history, even though it is the advancements. Let us have an overview of the system, power system. So in 1882, first DC system was installed in Pearl State system in New York, okay, New York City. So it is, as I said before, it is like a gap of two generations. Later on, after some years, like 11 years, I believe. So we have AC system installed. So that is also in North America, not in anywhere developing countries. It's all happening in the almost developed countries. So in 1920 we have thermal power generation units. Okay, so it was actually taken from the Kothari DP Kothari textbook. So this reference I made from the textbook. So AC network analyzer was actually the first special purpose computer, analog computer. So it was able to do the load flow studies uh, as like similar to the problem what we are dealing. So it was actually having some limitations, but this AC network analyzer was basically a large kind of a computer. So it is not actually made of transistors. So we know that transistor was actually discovered in 1947 Bell Laboratory. So the transistor kind of computer, whatever we are having, like laptop or desktop, facility was not available. So these computers look like a size of a room. Okay, it is like a large electromechanical devices, but it is able to do the calculations, complex calculations. So power system is identified to be dynamic. It is non-linear due to the trigonometric terms like cosine and sine, and we have voltage squares. So the solution power flow equation itself is identified to be non-linear, and at a time to solve a large power system, we need to do a load flow study. So load flow study was not feasible, not possible in those times. So even though we have discovered to use the electricity as the most important form of energy that is readily available, easily to be able to be transported, but the efficiency of the system was very poor. But in order to study the efficiency, we need to do some load flow studies. So we identified the problems, that is when we are connecting many generators so into the power system infrastructure. So we identified the generation units are to be operated in an efficient manner, but how to solve that problem? So there are many generators connected, and we have the famous economic dispatch problem, unit commitment problem. These are all the study on the power system, but there was lot of complexity involved in that. So they were unable to solve the transmission losses, power system transmission losses, the B coefficient, everything was not very clear. We were always approximating the generator characteristics, cost characteristics into quadratic terms, but still it is not very feasible because all those characteristics were non-convex input-output characteristics. That is, it is very difficult to find the solution for such problems. Even solution for such problems, even when we are using the mathematical techniques like Newton-Raphson method or because those methods involves derivations. Jacobian matrix is like first order derivative of the power, real power, reactive power in terms of voltages and the angle. So those Jacobian metrics were not converging in order to get the bus voltage levels throughout the buses. So it became bit difficult in those times. So what we power system researchers we started working on these problems, but these problems were very non-linear in nature, and to solve that problems, researchers identified evolutionary methods like you might have heard about genetic algorithm, particle swarm optimization, and all the other methods. Those are able to solve these nonlinear problems, and it is guaranteed to give approximately global optimum values. It is not accurate, but still it is approximately giving the required solution. So those were actually, there are so many beautiful journals published in that area. I am sure most of you are aware of such publications and you are more knowledgeable than me, but still I just want to reflect on to my ideas on power system. So these techniques like operation research that were very much used in World War II uh, were actually applicable onto power system problems, where we are formulating that into uh, we are solving it in the dimension of Euclidean distance, that is geometry of Euclidean geometry. So in 1950, Alan Turing was made a learning machine. Then only we realized there is a possibility of digital computers in solving real world problems like power system problems. So 1956, the first digital computer for the planning of power system problems, like we will theory and all we will study nowadays, that if you want to extend a power system you have to do the load flow studies. So that was actually recognized in 1956. So it has drastically simplified the complex problems with the help of computers. So computers has really helped in solving that nonlinear discontinuous problems faced in power system. Still we are finding new algorithms in solving such standard problems, like we might have heard about 14 bus system, 30 bus system, and Indian bus system and all. So those are all the standard problems. So nowadays we are adding new features like renewable energy sources, or we are adding many generators into the system to find the to minimize the power losses or efficiency of the system. So so these algorithms are basically called as meta heuristics. So heuristics so heuristics are actually a word derived from, it's a Greek word derived from, but the meaning of that word is to find, that is, it is always inspiring word for the researchers like me. So in 1965, first evolutionary strategy, that is one of the algorithm that was introduced in 1965, identified to solve a nonlinear problem very effectively. So it was taken from the reference, and genetic algorithm, that is one of the University of Michigan, 1970. John Holland, there's a book on genetic algorithm that is still famous, and it was actually researched, and we are aware of how the genetic algorithm works in solving such problems. Later on, tabu search was introduced in 1970, same year. Then we have neural networks introduced, Hopfield paper on neural network. So neural network is still advanced, and it is actually the foundation for deep learning or machine learning. So those are all derived from the, actually it is all within that characteristics of meta-heuristic algorithms. So we will be modeling neural network, and we will have so many learning algorithms. All those are derived from the first 1982 paper. Right? Then ant colony optimization, that is a recent, uh, there is a textbook on that also. And I could be able to find most of this textbook in our Anna Centenary Library in Chennai. These books are available because I have found myself I could able to get this anti-colony optimization textbook that is there in the reference section. I believe in the fifth floor it is available. So if somebody is interested, you can actually go and refer that. It's a very interesting textbook to refer. It was actually introduced in 1992, Mr. Dorico. So in 1995, particle form optimization. So this area is where this algorithm is where I have used in solving the problems I faced in power system. So this is how it is classified. This I have taken from Wikipedia. So this is a nice classification, I believe. Uh, so meta heuristics actually include all these uh, nature inspired algorithms such as particle swarm optimization and colony, and it is nicely classified evolutionary algorithms such as genetic algorithm, genetic programming, evolutionary programming, differential evolution. Most of my colleagues they are working on differential evolution, which I found to be very interesting, but definitely requires a lot of patience, I believe. Simulated annealing is one of the other method. So this is actually derived from the settling of iron, molten iron after settling. So these are all based on observation. So there is some stochastic local search. All these algorithms are actually very interesting, and these algorithms, what is one of the important characteristics of these algorithms are uh, an algorithm need to be tuned to solve the particular problem. So I fortunately I was able to tune my algorithm to solve the problem that I have solved based on my requirements. So it depends on whatever algorithm you are working. So that algorithm need to be tuned to solve. That is, you have to identify the parameters in order to make the algorithm solve the problem. That is actually finding global optimal solutions. So this is one of the example. 2006, NASA has solved the problem of antenna design. So and finally, genetic algorithm gave them a solution to look the antenna like this. So no, I don't think any mathematical problems can give such a solution. So using this solution, the antenna supposed to give them the features they demanded, like I believe maybe the high gain. So those things are possible using such genetic algorithms. It is actually it is kind of a black box approach. Uh, it is able to solve the problem, but we may not we know how it is working, but we don't know how actually it is able to give the solution. So these are all natural inspired algorithms. So these are basically inspiration we got from the nature. So whatever we are seeing, observing our surroundings, this is actually like it is not, it is actually evolved. That is the concept, scientific concept. It is not actually a creation. So in power system, the scenario was it's a cold start among researchers, right? So it is actually given in the reference 2007 because according to him, these algorithms research among the researchers where not very much rigorous research was happening in the power system, but it is the requirement because we are having a lot of problems to be solved in power system. So genetic algorithm is identified to have a good potential because we don't know which algorithm we have to select. So I was also so confused. I don't know which algorithm I have to do because there are so many algorithms and we don't know which method to be used to solve my problem. So mostly everyone will go for recent algorithms, but that is also not the correct way. Uh, but you can actually see the reference. So I was looking into reference, identified almost the genetic algorithm and particle swarm optimizations are giving optimal solutions. Some algorithms are like hybrids algorithms are available. So that will combine PSO and genetic algorithm to combiningly, and there is something called convergence time. So we want faster convergence as well as it has to give the optimal solutions. So such kind of analysis and approach, and the observation is genetic algorithm. There is something called binary genetic algorithm as well as continuous genetic algorithm. So I believe both are depending on the problem, both performance are uh, very good. And in power system, we know energy management system plays an important role. So energy management system is where we are putting our algorithms. So even if you take a microgrid or a power system in a substation level, there is a control room. Always in an industry also, there will be a control room, and they will have a SCADA, supervisory control and data acquisition. So those data are collected, that is real-time data, and it is monitored with the help of a SCADA system. And there is something called energy management system where we will put the algorithms to make the decisions. So if you know such decisions are taken, our systems are performing well. We are getting most efficiency out of the system, because these are all not. I mean, we cannot see it from our naked eye because it is happening, always happening in the background. So we don't know what is happening, how much voltage. We can only observe and we have to take the decision. So these algorithms are designed in such a way that it can solve the problems faced by uh, independent system operators or uh, whatever decisions we are taking on power system. So whatever algorithms you are working on, it should supposed to work in this energy management system. So what is the complete problem that address power system? If you say, what is the algorithm that will handle almost all the areas of power system? What is the algorithm that we need to put in the energy management system? So that is nothing but optimal power flow. So it has large constraints. What we mean constraints? There are so many variables and vectors. So the vectors that is already in our control, and there are vectors that are not in our control. So actually, optimal power flow is one of the important area in power system where it will solve the economic dispatch problem as well as load flow analysis combiningly, and it will give an optimal constraint. I mean, it will give an optimal solution meeting the constraints, such as we want the system not to be overloaded. So the constraints involved in optimal power flow, like equality and inequality constraints. Inequality constraints and are many. So we can actually add the constraints, and we can find the solution at particular instant. But if it is dynamic, it is changing for each hours, then we need faster algorithms. So still we are not in a position to find out an algorithm that will give an optimal power flow solutions. So almost a reason, I mean, from years, we identified interior point method, one of the mathematical method that is almost giving robust optimal solution for optimal power flow. So, but optimal power flow itself was introduced in 1960. So it is like one generation, you can say it is that much old, but this is the area I believe it has a very challenging opportunity, because actually optimal power flow can even include the consumers, that is the smart grid area. So if you are able to include the consumer choice also into the problem, that is energy management system can actually control uh, the generation side, that is utility, as well as the distribution side consumers. So that is the problem we have to work on. Okay, so next is how we used to solve this optimal power flow. So usually we used simplex method. We might have studied this in our PG, UG, or we might have studied the mathematical method of simplest method in solving the problems. And in 1984, interior point method was suggested. And there are other problem algorithms, mathematical algorithms like sequential quadratic programming, augmented Lagrangian methods. All these are actually able to solve the optimal power flow. And I believe interior point method is more emphasized. So this, if you understand, we can understand this mathematics, then we can find the limitations of such problems, and that such limitations can be overcome easily by evolutionary algorithms like PSO genetic algorithms. So just want to touch upon the mathematics, so I was discussing onto that. So in my problem, actually, in future I might be working on this responsive divan where I have to model a price-dependent load models. Uh, so I just want to, I don't want to discuss that right now. And please make sure that at least it is not shared anywhere, because this is my research work where what I am discussing with you. Maybe after 1 year or 2 years, we might be able to share that, right? Okay. So renewable energy integration. So that is one of the challenging area, because renewable energies are identified to be stochastic. It varies with the time. So what I have done, I identified such a renewable energy sources, the unit cost in a microgrid from the renewable energy sources are uh, cheap, or it is less costly. So I took that into advantage. So let us hope you have more renewable energy power generation, such as you have more wind or irradiation. Such scenarios we identified, and in such scenarios we were giving incentive to the consumers. So that is the area I was working on. So I was able to get some meaningful results from that. And actually, one of the paper got published on that area. That is, we proposed one of the novel real-time pricing strategy. So I hope I can able to explain that. So before that, let us see uh, what is the scenario of Indian smart grid projects. So Indian government had 14 pilot projects. So Pondicherry is one of the state union territory, that is where Pondicherry Electricity Department is combining with the uh, smart grid of India to have smart meters installed, as well as rooftop solar panels installed. So this particular illustration actually is proposed myself, where I identified we have basically power loads as well as the light loads. It is possible to modify the existing wiring system, and that is, we know there is power plugs in our home, so that can be connected to a separate meter, and this light loads to another meter, and we can actually convert these light loads into DC and power loads to AC, because in smart grid objectives we have something called demand response, where even utility need to control the loads. So in such scenarios, if the power loads are able to have a control feasibility, then it may not create any inconvenience where we are mostly depending on the light loads. And these light loads are actually working on DC supply. So this DC supply is supported by renewable energy sources. So I have one publication on this in IUP journal. And this particular concept, I find it very interesting, because we can actually convert the existing wiring that is rated for 5 amperes that is a single phase supply into, I believe it can be converted to 400 volt DC to meet or 110 volt DC to meet the requirements, because the losses involved also is minimized for the same architecture, so that I have shared. Okay, we don't have much time, I believe. So this is one of the, this is a illustration that here I have used 400 volt DC for the light loads, and we have three homes where one home is having a larger solar panel. This is a medium, and one home which doesn't have a panel. So this house consumers A can be a prosumers, that is, they can even sell the power. This consumer, I believe it is neutral because they are actually consuming the power they have generated, and this consumer is actually buying the power. So this is a nice comparison, which is possible in a country like ours, which I find very interesting because we may not face any power failures in such an infrastructure. So we are actually giving this 230 volt AC, that is for the power loads, because we are actually, even though we are saying our consumption is increased, we can see there is a drastic change in the efficiency of the devices. So the light loads are actually more efficient, and they are able to consume less power, that is 800 watts. That much power might be the typical consumption of a DC supply in our home. So it is actually possible for us to uh, for us to have a continuous supply without any interruption from the DC supply, without depending on the grid. But the grid is into better electrification, so it can actually meet all the demands, and it can do all the smart grid objectives like demand response, everything. That is the that is the idea what I have proposed. So what is the introduction of a smart grid? A smart grid is an electricity network. It can intelligently integrate the actions of all users connected, such as generators, consumers, and it can efficiently deliver a sustainable, economic, and secure electricity supply. So it is taken from distributed generation by Jenkins. So that is one of the definition of smart grid. So we have so many definitions. So smart grid services are identified to accommodate all the sizes of generations. It allows consumers to take part into market scenarios. It can provide information of choice to the consumers. Actually, we know our Android mobile phones can be very interactive, so it is possible. So significantly reduce the environmental impact, because if the thermal power generation, as we said, 65% or 70% of thermal power generation, if you are able to reduce that, that itself is a good sign that we have we are having some control over carbon emission. Even though electric vehicle, that is also one of the dimension which can significantly reduce the carbon emission. So when we compare the smart grid and microgrid, where smart grid is a variety of operational states. So as the smart grid, the features are increased, we will have lot of constraints. So your optimal power flow problems will have so many constraints that become impossible, or it is very difficult to solve using conventional mathematical methods. So there only we are proposing the evolutionary algorithms, and it is actually taken from the Federal Energy Regulatory Commission. And when we compare that with microgrid is actually a small grouping of sources, and it may be connected with a central grid, or it can be a isolated standalone system. So these are all taken from some reference, U.S. Department of Energy. So when we compare existing grid to smart grid is digital two-way communication, distributed generation is encouraged. There are more sensors, so we have more operating states. It is self-monitoring, self-healing, adaptive. It has throughout control is possible. Even one device can be turned on and turned off. So there are many choices for the consumers. That is the direction of smart grid. This is all just a comparison. So energy management system. So in the energy management system, we are actually having so many modules like forecasting module and the storage system, and there is optimization module, right? So this is actually handled by energy management system, and it is actually communicated within the SCADA system. So this is the proposed layout. This is what I have proposed in a microgrid. We have an energy management system, and you have residential load because I'm taking only a load that is in the range of 100 kilowatts. So we are assuming we are taking this because in our country we are identifying some areas with consistently we are facing power failures. So that those areas are mostly remote villages. So if you are able to make a microgrid scenarios, sorry, if you are able to give a microgrid scenarios for such areas, it can actually solve a lot of problems. So this is actually a micro turbine, fuel cell, and renewable energy sources, and we are able to get forecast signals, that is the future day ahead load, and this energy management system will schedule the fuel-based sources in such a way that we are having an economy of power generation, as well as the consumers will have a choice of a real-time pricing. So that is actually, it's a problem formulated from this layout. So this is the real-time pricing, and we know that in smart grid we will have a communication infrastructure called advanced metering infrastructure, and it has some protection and management system. So what I identified, the cost of wind power is $0.074 per kilowatt hour for wind energy, as well as for solar it is 0.125. It is taken from the Department of Energy. So when I used that to calculate the economic dispatch problem within this uh, microgrid and fuel cell, what I identified, actually the cost of power generation from wind and solar is uh, lower than the fuel-based sources in a microgrid, but it is not the case for the conventional power generations like thermal power generations. It may be higher, but in the microgrid scenario, I identified this cost is higher than the renewable energy sources. So we took that into advantage and we proposed a real-time pricing strategy. So this strategy has many characteristics that will meet the smart grid objectives. Okay, so this is one of the typical load profile I have taken. This is actually taken from a reference that might be available in my future thesis. That's for 24 hours. So that has taken a reference, as well as I have taken the power generation from wind as well as solar. This is also taken from a reference, so that we can generate the data and we can analyze for a better answers in the future. So that is why I have taken such a generation profiles. So for the same photovoltaic generation, we have used this formula. So I'm going to skip because sir has given me a time of 11:30. So I will try to make it a bit faster. I'm almost finishing. I believe the slide number is almost finishing. You can't see the slide number. Okay. Okay. So this is the pricing strategy that I have proposed. So if I explain this strategy, this is actually we are having something called, what you are looking at is called power to cost index. So this dotted line represents a value of 6.69. So that is actually an average power to cost index that I have taken as a reference. So for a particular hour, if the power to cost index is crossing this reference, that time period we will give incentive to the consumers. Similarly, if it is not crossing, then the incentive is not given. So as I said, power to cost index. So power generation, that is a power demand, and the cost of that particular power generation. So if let us assume we have more renewable energy sources, then obviously the power to cost index will increase because we identified the renewable energy sources cost is less than the fuel based sources in a microgrid. So if you have more renewable energy sources, by the virtue of renewable generation, we have more, that is, this is actually crossing the index. So that is taken as advantage. That means one more application is, let us say, if you reduce the power demand for the next hour, somehow the consumers are able to reduce the power demand. If you send some message like, if you reduce the power demand, we will give you some incentive. Then also the power to cost index will increase because you will have significant reduction in the fuel based sources power generation, because for a given renewable energy power generation, if you reduce the fuel based sources power generation, then the power to cost index that will cross this limited this index this reference. So it is able to cross the reference if you reduce the power also, as well as let us assume you are lucky and you have more renewable power generation. Such scenario also it will cross. So those time periods are identified. That means all this green indicates the incentive periods. So the consumers are given some incentive. So that is a percentage of benefit from the renewable energy sources. That is the real-time pricing that we have proposed. It happened to be very advantageous because it can actually reduce the peak. That is, if you say there is some peak demands and you want to have a control, it is possible by this real-time pricing strategy. It is very intuitive, it is very easy to understand. In that way, the consumers will accept such a strategy, and it is actually helping the utility by minimizing the uh, cost of, by meeting all the demand, as well as minimizing the thermal power generation or reducing the fuel, that is called your carbon emission, everything. So this has so many advantages that I can list out one after the other. So this is one of the pricing strategy that we have proposed. I have proposed in my research. So it's a novel strategy. It has given hourly incentive to the consumers. It has a control over consumption. It is depending on the behavioral response of the consumers. It can reduce cost, emission, and it can bring economy in the microgrid. So it is a overall control. It's an elegant approach that we are going to propose. So what we identified, to now put it in a nutshell, my research is the problems in power system are non-linear. There are so many opportunities awaiting, and if you are doing the simulating models, it will give some better understanding on the power system. And we are always in need of fast converging algorithms. Evolutionary algorithm satisfies present requirements of smart grid challenges, but we have to experiment more evolutionary algorithms in realistic power system to solve, to get almost required, desired results. So these are all some of the reference. So parallel particles from optimization proposed by my guide himself, and Venkatesh and Jnanadas sir proposed one of these, that is application of evolutionary algorithms. It's actually one concept they have included in this. They changed the multi-objective problem into a single objective problem. That is very interesting to refer from that publications. Okay, so this is one of the interesting publications that I found very interesting because it has taken high wind scenario into the consideration of real-time pricing. So this has actually inspired me, this particular publication, in putting forward that real-time pricing.